Assalamualaikum. Today we are going to start the section 16.3 of the chapter 16, and this is about fundamental theorem of line integrals. So in this section we are going to learn fundamental theorem of line integrals, and then we have some results about conservative vector fields. So before starting the fundamental theorem for line integrals, let's have a look at the fundamental theorem of calculus. Uh, and according to the fundamental theorem of calculus, we have this result: integral from a to b, f prime x dx is equal to fb minus fa. Now here f prime x is the derivative of fx, so f prime is actually rate of change of fx, and along with the condition f prime is continuous on ab. Then this theorem gives us the net change, that is total change. Now integral of rate of change is the net change. It makes sense. So theorem 2 in your book, fundamental theorem for line integrals. Let C be a smooth curve given by the vector function Rt, where T lies between A and B, and let F be a differentiable function of 2 or 3 variables whose gradient vector is continuous on this curve C. Then the line integral of along the curve C del f dot Cr is equal to f of Rb minus f of Ra. That is the value of f at the endpoints of the interval. So RB is the terminal end of the curve C, and RA is the initial end of the uh, curve C. So this is quite similar to fundamental theorem of calculus. Now, theorem 2 says that we can evaluate the line integral of a conservative vector field, that is the gradient vector field of the potential function f, simply by knowing the value of f at the endpoints of C. In fact, it says that the line integral of del f is the net change of f. Now, in the previous section we learned that a field is conservative, a field f, vector field f is conservative if there is a potential function f such that f is equal to del f. So that is why we can conclude this, that we can evaluate the line integral of conservative field simply by knowing the value of f at the endpoints of C, right? Another observation: if f is a function of two variables and C is a plane curve. Okay, curve can be a plane curve or a space curve. So if C is a plane curve with initial point A x1 y1 and terminal point B x2 y2, so according to theorem 2, we have the line integral of del f dot dr along this curve C is equal to the value of f at the terminal end, that is x2 y2, minus the value of it at the initial point, that is x1 y1. Okay, if f is the function of three variables, then C is a space curve joining the points a x1 y1 z1 and b x2 y2 z2. So, then the fundamental theorem of line integrals takes this form. Okay. Now the next definition: path. Suppose C1 and C2 are two piecewise smooth curves. Okay, these curves are called paths that have the same initial point A and terminal point B. So we know from example 4 in section 16.2, and I think I solved this example in the previous section or in the previous video. We observed that f dot dr was not equal to f dot dr along C2. That is, f dot the line integral along different curves of the same vector field was not equal. Okay, but in case of conservative fields, this is going to be equal. And from the fundamental theorem of calculus, fundamental theorem of line integrals, we can conclude that the integral along C1 of del f dot dr is equal to line integral of del f dot dr along C2, where del f is continuous. That is, the line integral of a conservative vector field depends only on the initial point and the terminal point of the curve. It does not depend upon the path, actual path. It just depends upon the initial point and terminal point. So this leads us to the idea of independence of path. So in general, if f is continuous vector field with domain D, we say that the line integral f dot dr along the curve C is independent of path if f dot dr along C1 is equal to f dot dr along C2 for any two paths C1 and C2 in D that have the same initial and terminal points. So this means that line integral of conservative vector fields are independent of paths, and this is actually the immediate consequence of fundamental theorem of line integrals. So, or we can say that let f be the field defined on an open region. This is an open region D in space, and suppose that for any two points A and B in D, the work done by the force F from A to B F dot dr in moving from A to B is same over all the paths from A to B. Okay, whether it takes this path, whether it is along this path, whether it is along this path, or it is along this path. For every path, f dot dr, the integral of f dot dr is the same if the field f is conservative on D. Okay, so then the integral f dot dr is path independent in D, and the field f is conservative on D. So these are the actually this is the same thing we are repeating in different forms, we are repeating in different words, or we are approaching towards same thing in different ways. Okay, so just to make understand the idea. Now, what is closed curve? A curve is called closed if its terminal point coincides with its initial point, that is RB is equal to RA. So this is an example of the closed curve. So next theorem is again about the line integrals, and according to this theorem, line integral along the path C f dot dr is independent of path in D if and only if f dot dr along C is equal to 0 for every closed path or closed loop C in D. Closed path is sometimes called closed loop as well. Okay, so this is another result about the line integral. So the line integral of f dot dr along the path C is independent of path in D if and only if f dot dr along C is equal to 0 for every closed path or closed loop C in D. So if we have a path like this, we have 2 points. C1 is a path from A to B. There is another path C2 from A to B. But if we want to make these two paths a closed path or a closed loop, so we can reverse the direction of one of the paths. So if we reverse the direction of C2, then we have a closed path. We will start from A and we will end up at A. Okay, so initial terminal point becomes same. So if we have two paths from A to B, one of them can be reversed to make a loop. So we just change the direction of one of the paths from B to A, right? Okay. If A and B lie on a loop, we can reverse part of the loop to make two paths from A to B. Okay, so if we have a loop uh, which starts from A and ends at A, and we have some point here B, we can make two paths from A to B by reversing, of course, one of the portion of the loop. Now, physical interpretation. The work done by conservative force field as it moves an object around a closed path is zero. So, the physical interpretation of this theorem, theorem number 3, is the work done by a conservative force field as it moves an object around a closed path is zero, right? Okay, there are a few more definitions which are going to be used in next theorem. A region D is said to be open if for every point P in D there is a disk with center P that lies entirely in D. So D does not contain any of its boundary points. This idea is actually just an extension of open interval. So in open interval, whenever we choose a point in the interval and we draw uh, an open interval centered at that point, then the whole subinterval will be contained in the open interval. So such an interval is called open interval. But in case of closed interval, if we take a boundary point and we draw an open interval centered at boundary point, then the whole interval is not contained in the closed interval. So that is why that is called closed interval. So similar idea is extended in the closed open region. So a region D in the plane is said to be open if for every point P in D there is an open disk centered at P that lies entirely in D. Okay. Next definition, a connected region. A region D is said to be connected if any two points in D can be joined by a path that lies in D. Okay. A region D is connected. I'll show a few figures of connected regions later on. A region D is connected if any two points in D can be joined by a path that lies in D. Okay. So actually these definitions are going to be used in theorem number 4. So that is why we learned these concepts. So theorem number 4 states that suppose F is a vector field that is continuous on an open connected region. Open connected region D. If F dot dr along the curve C is independent of path in D, then F is conservative vector field on D. That is, there exists a function F such that del F is equal to F. So this implies the following statements are equivalent. That is, if the line integral F dot dr around every closed loop in is equal to 0 around every closed loop in D, then the field F is conservative on D. Okay. So suppose that F is a vector field that is continuous on an open connected region D. If F dot dr is independent of path in D, then F is conservative field on D. So that is, there exists a function F such that del F is equal to F. And this is just a remark, not connected with this, but you should remember this for further applications. Okay. Now we are talking about conservative vector fields again and again and again. But the question here is, how is it possible to determine whether or not a vector field is conservative. So this theorem gives us the answer. Is fxy is equal to pxy I plus qxy j is a conservative vector field where p and q have continuous first order partial derivatives in domain D. Then throughout D we have partial p over partial y is equal to partial q over partial x. Okay, if f is a conservative field, okay, if f is a conservative field, then this condition is satisfied. Now the converse of this theorem must be like this: if this condition is satisfied, then f should be a conservative field. But for the converse, a few more conditions are required for the converse to be true. So let's see what are the conditions. So first, let me read it again. If f is a conservative field, if f is a conservative field, then there is a potential function f such that f is equal to f. Okay. Then this p, if f is equal to del f, then this p is actually partial f or partial x, right? And this q is in fact partial f or partial y, because this f is equal to del f, right? And del f, is partial f or partial x I plus partial f or partial y j. So p here is partial f or partial x, q here would be partial f or partial y. Now by Taylor's theorem, partial p by partial y becomes second order derivative of f with respect to uh, of partial 2f by partial y partial x. That is the second order derivative of this function with respect to y, right? So partial p by partial y is equal to partial 2f by partial y partial x, and this is equal to partial 2f by partial x partial y by the Taylor's theorem, and this is nothing but partial q by partial x, right? So that is why this result holds. If f is conservative field, then partial p by partial y is equal to partial q by partial x. Okay, the converse, I already told you, the converse of theorem 5 is true only for a special case, a special type of region, specifically simply connected region. So what is simply connected region? A simple curve is a curve that does not intersect itself anywhere between its endpoints. So this is simple curve, but this is not closed. This is not simple, not closed. This is simple closed curve, and this is closed curve, but this is not simple. Okay, according to this definition. Now the simply connected regions. A simply connected region in the plane is connected region such that every simple closed curve in D encloses only points in D, right? So this is simply connected region, because whenever a simply connected region is the plane is a connected region D such that every simply closed curve in D encloses only points in D, right? So if we draw any simple closed curve in this region, it will enclose the points of the region. But in this case, if we draw a simple closed region like this, let me draw it here. This is a simple closed region, right? But it does not contain only the points of region D. It contains this whole as well, and these are not the points lying in the region D. Okay, so this is not a simply connected region. Similarly, this is not a simply connected region. Similarly, this is not a simply connected region, because when we draw a curve like this, a curve like this, so it does not contain only the points from the region. Okay, so intuitively it contains no hole. A simply connected region is the region which contains no hole and cannot consist of two separate pieces. Okay, So simply connected region looks like this. And now the converse of theorem number 5, let F be a vector field. So F is any vector field. Okay. So finally, we are going to uh, have a theorem that which gives us the condition for a vector field to be conservative. So let's see what's the condition. F is equal to pi qj be a vector field. This is any vector field on an open simply connected region D. On an open simply connected region D. Open region means it has no boundary. Simply connected, we have already seen that what is the simply connected region. D. Suppose that P and Q have continuous first order derivatives and this condition holds, that is partial P by partial Y is equal to partial Q by partial X throughout D. Okay, for every point in D this condition holds, then F is conservative. It means then there exists a potential function F such that this vector field F is equal to del F, right? Okay, next example, determine whether or not the vector field fxy is equal to x minus y I plus x minus 2j is conservative. Okay, so p here is x minus y, okay, q here is x minus 2, then partial p by partial y is equal to minus 1, partial q by partial x is equal to 1, and both are not equal. So f is not conservative by theorem number 5. Okay, next, determine whether or not the vector field is conservative. Again, p is given by this function, q is given by this function. So we have partial p by partial y is equal to 2x, partial q by partial x is also 2x, and the domain of f is entire plane D is equal to r square, which is open and simply connected. So this is important. This condition is not only enough to prove that this vector field is conservative. Along with we have to check whether the domain satisfies the conditions given in theorem number 6. So domain of this vector field is entire the plane R square, because this is defined everywhere, which is open and simply connected. Therefore, we can apply theorem 6 and conclude that f is conservative, right? Okay, now next target. Theorem 6 told us that f is conservative, but it did not tell us how to find the potential function f such that f is equal to del f. Now the proof of theorem 4 gives us a clue as to how to find f. So we use partial integration as in the following example. Okay, we learned the procedure with the help of this example. So let's see how can we find the potential function if a conservative field is given. So if fxy is equal to 3 plus 2xy I plus x square minus 3y square j, find the function f such that f is equal to del f. Now we have to find this potential function. Now evaluate the line integral, part B, evaluate the line integral f dot dr along the path C, where C is the curve given by this vector. Okay, first we'll find this f and then we'll solve part B. So we know that f is conservative. We just have seen that f is conservative. So f is conservative. This is known. So there must exist a potential function f such that del f is equal to f. Now, as we have already discussed, that if this is a conservative field, then there is a potential function f such that del f is equal to f. That is, this p is equal to partial f by partial x. So partial f by partial x is equal to 3 plus 2xy, okay, which is equal to p. Now q is equal to partial f by partial y. So partial f by partial y is x square minus 3y square, right? Now we'll partial integrate in order to find the f. So first we'll integrate this fx. Okay, let me write fxy on the next slide. So let me write here fx xy is equal to 3 plus 2xy. Okay, 3 plus 2xy, and fyxy was x square minus 3y square, x square minus 3y square. So we have these two equations, and sorry, we have to find the value of f, and this is in fact p of f, and this is q of vector field f. Okay, so first of all, we integrated this equation. Okay, this is partial derivative with respect to x, so we integrated this with respect to x. So while integrating with respect to x, we will keep y constant. Okay, so the integration of 3 with respect to x is 3x, and integration of 2xy with respect to x is x square y, because this is x square by 2 times x square by 2 into y, so it will be x square y plus some constant. Now since y is constant, some constant with respect to x will be a function of y. So this is the partial integration of this function. Now notice that the constant of integration that we have already discussed. Now original fy, which we deduced from the vector field, is given by this function x square minus 3y square. Now differentiate this with respect to y, we have this. Okay, f is given by 3x plus x square y plus gy. Now differentiate this function with respect to y, we have this. Now with respect to y, 3x is constant, so derivative of 3x is 0 with respect to y. Now with respect to y, derivative of this function is x square, and derivative of gy with respect to y is g prime y. Okay, so this is in fact equal to x square minus 3y square, because partial derivative of the function f is given by x square minus 3y square. Okay, now by comparing, we have g prime y, we have g prime y is equal to minus 3y square. Now in order to find gy, we have to integrate it with respect to y, of course. So we have gy is equal to minus y cube plus k. So our fxy is equal to, now just plug in the value of gy in this fxy equation number 9. So our fxy is equal to 3x plus x square y minus y cube plus k. So this is the potential function f. Now let's solve the part B. To use theorem number 2, all we have to know are the initial and terminal points of the C, namely r0 and r pi. Okay, and the line integral of f dot dr along the path C is equal to del of, since this field is conservative, so that is why we can use the fundamental theorem of line integral. So this is equal to a line integral del f dot dot dr, and according to fundamental theorem of line integrals, we have the value of this line integral is equal to the value of f at the terminal end minus the value of f at initial end. So this is equal to 3 e to the after some simplification and manipulations, we have e to the power 3 pi plus 1. Now example number 5, if fx y z, now this is an example in space, that is the function of a vector field of 3 variables. Fx y z is equal to y square I plus 2xy plus e3zj plus 3y e3zk. Find a function f such that del f is equal to f. Again, this is p, that is partial f by partial x is given by y square, partial f by partial y is given by 2x plus e to the power 3z, partial f by partial z is given by 3y e3z. Since this is conservative field. So we have to we have del f is equal to f, and so p is equal to partial f by partial x, q is equal to partial f by partial y, and r is equal to partial f by partial z. So first of all, integrate this with respect to x. So we have fxy is equal to xy square plus gyz, because we are integrating with respect to x. So y and z will be constant with respect to x. So the constant of integration will be the function of y and z. So gyz is the constants. Now we'll differentiate it with respect to y. Uh, f y x y z is equal to 2xy plus derivative of this function with respect to y. Okay, now equating this, we have equating this fy with this fy. We have gyYZ is equal to e to the power 3z. So gyYZ is equal to e to the power 3z. Okay, now integrating this with respect to y, we have gyz is equal to ye3z plus h of z. Now, since g by z is a function of y and z, and we are integrating this with respect to y, keeping z constant, so constant of integration will be a function of z. So gyz is equal to y into e3z plus hz. Okay, now fxyz becomes xy square plus ye3z plus hz. Now, in order to find hz, uh, we will differentiate it with respect to z and compare it with this result, which is the actual partial derivative of f with respect to z. So by doing this, we have hz is equal to constant. So you can do this simple mathematics, and so our potential function will be xy square plus y e to the power 3z plus k, where k is any constant, and that's all. So rest of the things we'll discuss in the live session tomorrow, inshallah. So please go through all the theorems in the article 16.3 to make uh, it more understandable, and to have deeper insight of the topic. So see you tomorrow, inshallah. Take care. Bye bye. Allah Hafiz.